What's the difference between f of 3 and the limit as x approaches 3 of f of x? We're going to focus in this video on looking at this for the graph of a function. This is one of the hardest ideas in calculus, and if when you first see it, you don't quite grasp it, and you need some practice, that's totally normal. I'm going to encourage you to stick with it and be patient, because once you master this concept, you will find that it unlocks a lot of doors in calculus, and you can also feel very proud of yourself. First, let's talk about how to evaluate a function at a particular value. And in this case, I'm just going to focus on x equals 3. When we want to evaluate f of 3, what do? In the graph, to evaluate the actual function value is for a closed circle at x equals 3. A closed circle might be drawn in a way to make it conspicuous. If there's an open circle, we usually make the closed circle a bit bigger to emphasize where the function value actually should be found. But in a normal function, a continuous function, you also have a closed circle. It's just that it's not really big. It's a closed circle where the curve just continues through it. So in looking for these, you want to look at the y coordinate of this closed point. At x equals 3 for this a of x, this is the point 3, 4. So my a of 3 value is equal. Similarly, on b of x, when I look at x equals 3, I'm looking for this closed circle, which occurs at the coordinate 3, 6. So that tells me that b of 3 is equal to 6. The same thing with c of x. Even though this is a discontinuous piecewise function, all that matters when evaluating at x equals 3 is where is that closed circle. And again, with this function, I have this at the point 3, 6. So c of 3 is equal to 6. This often throws people a bit, so just to emphasize, if you see an open circle and a closed circle, and you're trying to evaluate the function, look for the closed circle. In this graph, there's an open circle and a closed circle. At x equals 3, we care about the closed circle. This happens at the point 3, 9. So q of 3 is equal to 9. The fact that there's this open circle just tells us don't look here for the function value. But what if we see something like this where there isn't a closed circle? There's only an open circle. If there's no closed circle on the graph, the function is undefined at that point. So here at x equals 3, we look and we see there is an open circle but no closed circle. So that's the mathematician's way of saying that this function does not take a value at x equals 3. Now let's talk about how to recognize the value of the limit. This is pronounced limit as x approaches 3 of f of x. What it means is something different than the function value. How can you tell the limit? There are basically two situations we can look at. We're going to ask near x equals 3. So in this tiny little strip that includes x equals 3, right about here in this tiny little strip, is the graph in one piece or two pieces? And we're going to ignore what actually happens at x equals 3. So maybe a better drawing would be like, if I ignored x equals 3, if I ignore the whole, this is just like one piece. So you have to ignore the whole and say, if I ignored the whole, is this graph in one piece or two pieces? Even if I ignore the whole in this situation 2 graph, this curve is in two pieces. So this is a very important distinction, and we're not concerned about what happens at x equals 3. So you want to look at these two different situations. And if you're looking at the situation where the curve is in one piece, except for potentially a hole, then the limit, then we can look at a second question. Second question is, if the curve is in one piece, is there an open circle at x equals 3? And if there isn't, if the curve just looks normal, like most of the graphs that we've drawn in the past, like right here, it's continuous through x equals 3, then in this situation, the limit is equal to the function value. So all I have to do is look at the point that is actually on the graph in this situation. So I have a point here at 3, 4. And so in this case, both of these numbers would be equal to 4. So something that looks like this, where if I ignored the open hole, I could go through it. The limit value at x equals 3 will be equal to the y coordinate of the open circle. So that looks like this. Here I have a open circle at 3, 2. And so in this case, limit as x approaches 3 of f of x would be equal to 2. There is no closed circle here, so it's actually the case that f of 3 is undefined. That doesn't really matter in terms of finding the limit. Same type of picture. Here we have an open hole, but we could go through the open hole in one motion. So at x equals 3, there is an open circle, we could go through that open circle just straight through. It doesn't matter for the limit that there is a closed dot somewhere else. In this case, what we're looking for is the y-coordinate of this open circle. So this open circle is at 3, 6, and the limit as x approaches 3 of this function would be equal to 6. F of 3 is equal to 10. That doesn't change anything about what I just said. The limit is where we think we're headed, or where the trend in the y values is as x approaches 3. If the curve is in two pieces outside of where you're looking in terms of the x, where it's like, all right, oh, I got to jump. In this situation, the limit does not exist. So I can't go straight through the open circle without doing some kind of teleportation business. If your curve is in two different pieces, it doesn't really matter whether there's an open or a closed circle or top or bottom, whatever. If it's in two pieces, then the limit at that x value, and it breaks at that x value, then the limit at that x value does not exist. And the key idea here is to evaluate the limit. All that matters is what happens really, really close on each side, but those two things have to be the same. And in this case, from the left-hand side, it's not approaching the same value as the right-hand side. We'll talk about that more in another video.